Good evening, everyone. My name is Dishan Ahmed. I'm a professional structural engineer for the last 15 years. I've been working in this field. I've used different kind of softwares: SAPs, ETAB, Save, Autodesk Robot, and STAAD. Hands down, STAADpro is one of my favorite because I can optimize it. I can make it work the way I have been taught in university and get a lot of manual calculations. So I started designing my own. In my line of work, I had to design a lot of complicated slabs. So I've created this software. It's called Openslab. You can see in the link in the description that where you can download this from. There's a small fee to it for buying it if you like it. Uh, yes, it costs a lot to get a software developed. But anyways, I'll get down to it. If you ask me, this is one of the only tools you'll ever need to design any kind of slab: one-way slab, two-way slabs, curved slabs, arch slabs, sloping slabs, slab on grade, anything at all. If you want to design, this is the only tool that you need, and it is going to be so easy. And I'm just going to demonstrate how I do it. If you're familiar with STAAD, it's very easy. It's very simple. If you ask me, it's very simple to model in it. It's easier than any other software that I know, but obviously everybody gets used to it. We're going to explain using this example. This is an ACI 318. Open slab right now is only available in feet and kips and pounds. I'm sorry I haven't converted the units to the metric units, but this is an example. This is an example of a one-way slab. You can see this is the span. It's a simple slab. There's an exterior span, there's an interior span on this direction, and this is the base spacing. So the one-way slab is in this direction. We're just going to examine how easy this is to design in our Openslab. So let's get into it. I'll try to do this as soon as possible, and you'll get to see that how quickly you can do this. So the slab span, and these are the loadings. Beam spacing is 18 feet, and thicknesses you can get from the allowable table. I'll get to that in a while. And so this is the software. So we can now go on to, we just try to model only two spans, I guess, and that should do the job. Right, so the center of the support is 16 feet, and length is, I guess, not specified here. I guess in one-way slabs, if it's anything more than twice, then that's about it. So it's 16, so we'll go with the column spacing of, as a matter of fact, there's a single beam, so this is the whole span. So let's take this as 60, and then this is as per specification in this example. It's 16 feet. Here you can see this. All right, let's model this. So I have my model going to go on like this: 16, 16, 32, 32, and 16. I'll take 48. And the span of my one-way slab is 16. So I'll go 16 in Z direction. And there you go. So this is my entire panel. And I'm just going to do that. So the most important thing that we have to take care of here is the orientation of the slab. Right, there you go. I've just popped up this tool, Openslab. If you go in the help tab, you can see that the orientation of the plates in STAAD should be like the plate in diagram on the left. This means Y should be like this, X should be like this, and Z should be upwards. This would happen if you start from the lower left corner, always from here to here, and like this. Let's check out our orientation. Does it match? It does or not? Yes, it does. So this is very important. This is the most critical, actually. This is the only thing you have to take care of, that this orientation matches this orientation. Moving on. So this is my slab. This is a one-way slab. If I'm modeling one-way slab, few of the engineers that I know, they don't like to model beams, because beams in finite element analysis pose flexibility, which is the elasticity in the beam. If we want to ignore the elasticity in the beam, just like we get to see in the book examples and the example like this, we simply assign this as support. So right now I'm just going to go ahead and mesh my slab. Right click this, generate mesh. It is going to be a quadrilateral meshing, and as per ACI, it designs 1 feet strips. So we want to do a mesh of 1 feet by 1 feet. So I see the divisions here are 16, so 16, 48, 48, 16, and 48. Simply mesh it. There you go. I'm going to switch off the orientation so that we can be a little clear on this. So now the orientation is gone, and that's that. So I am going to, in order for this to be a one-way slab, I'm just simply going to add pin supports here and pin supports here. Right then, and supports, and create, and pin. There you go. The second thing I have to see is that thickness of the slab. Simply supported, one-way continuous, both end continuous. I'll go with 24 right now. These are for deflections. You can study more about them in the ACI code. But right now, I'll go with the thickness that the book, the example has specified. It is using 6, so use H as 7 inches. Right then, so I'm going to do the thickness. Keep in mind, we're going to use H here, not D. And sorry, I'm going to assign the property thickness. So 7, I'll use unit converter, 7 inches. There I go, in feet. And that's that. Now the only thing left to do is assigning loads to the whole slab. Let's assign load to this plate. So if you want to create load cases and then combinations in STAAD, that's your thing. But right now, for the example's sake, I'll just go ahead and create just a simple load case and apply a load to the slab, plate load, and GY direction. And what is the value? The entire load with all the factors included is kips, should be actually kip per SFT. It says kip linear foot, which is a little weird for an example, but anyways, we'll use this load. This is just an example I bringed out from the internet that I thought it would be easy. So anyways, so load is 0.288 kip minus 0.288, add and apply to my slab. Assign. There you go. The model is complete. Let's add an analysis here. Okay, and I'm going to run the analysis again and see if there are any warnings or not. Nope. All right, there you go. I'll also add this stat file in the comments so you can download this and study it. Anyways, going to the post processor, very simple, and I go to my plates, and if I want to see the load case and MY or MX, maybe I'll just write MX. But I don't need this. This is the magic. This is where my magic starts with my handy little tool. Right then. So the maximum span is basically over here, and then over here. Since I haven't modeled a continuous, so it's just an edge thing. So we'll just design this reinforcement here and reinforcement here. So all I do is I select this and press analyze. That's it. Now let's go here. MX. MX. Keep in mind, this is not the global coordinate system. We are going to be going through the local coordinate system. So if you want, if as a reminder, this is Y in this direction, and this is X. And when STAAD or this Openslab tells you MX, this means moment in X direction, not about X, but in the X direction. So this is X. So moment in this direction, if you see globally MX about X, but locally it's in the X direction, is minus 9.122. This will tell you the minus sign. If you go to the help tab, negative moment requires steel at the bottom layer. Positive moment requires steel in the top layer. This is just how STAAD works. This will give you the negative in the bottom. So it will, this number here, this notation here will tell you if it is bottom steel or not. Right. So MI, M and X is red highlighted. This means that the steel in X direction, number 3 at the rate of 6 inches, is insufficient. So what do? I increase my steel dia maybe and analyze it again. Right. This is good enough. So MX applied is minus 9.112. MN, which is allowed, is 10.09. So number 4 and 6 would easily suffice. Verify our model according to there. So let's do this. If we can do this very easily, we can just simply select the entire model and repeat it, transitional repeat in Z direction with 16 feet, and this should do the job. There you go. We've added another span, and I think this should do the job. Yeah. Let's check for some duplicates if there are any multiple structures. No. Delete duplicate highlights. No. So that's fine. Let's check if the load is transferred to the other slabs as well. And I presume it has had. Okay. Sounds good. Let's run analysis here. No warnings, no errors. Now let's see what our moment is telling us. I like to put this in MX. And now our values should be matching to what we have in the mid span over here. This is the mid span. This is the mid span. You can see. There you go. So the mid span, the value is my 5.12. Let's look at the example. We have 5.83, which is pretty close. This is just a moment of coefficient method, and right now we have a very precise FEA model here. And on this support, let's see what is the value here. Minus 0.71, or approximately 0. Okay, now this value is 3.14 because it's on the face of the column. Remember, we haven't designed the face of the column. So if we go here, this is our face of the column, face of the beam, sorry, 0.223. So this also is pretty close. Keep in mind, FEAs are always different. So the highest value it is showing is on this support, the middle support, 8.17. Let's see what do we have. Very close again. We have 7.8. And we have our steel sufficing. So now if for the continuous, I think I'll go with number 4 at the rate of 8 inches. No, it's not working. It's going to be 9 inches. 7 inches maybe? 7 is fine, but since it's 7, I like it to keep it 6. So yeah, that's fine. So what about this span? I should be having the same results. This. What I try to do is I try to follow the bed, the stress bedding here, the stress contouring here, and try to pick out the maximum since the dark purple is the maximum. So I try to follow that. So this is a one-way slab. So now you see that the values are pretty much close to our example over here, and the design is there. Again, as I told you, now that we are in a continuous method, so the shear, if you see, is 2440 pounds. That's 2.4 kips. Let's go back to the example and check out the shear. So shear, the value that we get is 2.244, and the value that we have over here is 2.79. Pretty close. Keep in mind, moment coefficient method and these manual calculation methods are very empirical. The precise results is what are obtained from your FEA models. So there you go. Anyways, this is a pretty good example. I'm going to send a link for this over here as well. So if I look at the section number 4 at the rate of 9 inch, as per my calculation, number 4 at the rate of 9 inch is barely making it. If I have to design it on this side, or is it? Oh, it's actually making it very nicely. Because it's here, I have minus 5.19 and 6.97 as my MN. So excellent. So this is good. So number 4 at the rate of 9 inch. And this is number 4 at the rate of 12 inches. As I said, theoretically we have 0 value, but this is for detailing. You can use number 4 at the rate of 12 inches or maybe number 3 at the rate of 9 inches. And the negative is number 4 at the rate of 8 inches. That's as I said, we tried. This is L/4 curtailment rule. So let's check out the value here. 6.97. This goes red if it is insufficient value. Let's try 8. No. Let's try 7. Yeah, 7 is good. So the only difference in this example reinforcement is this number 4 at the rate of 8, and we have a number 4 at the rate of 7. This is to illustrate that Openslab can be a magic genie for designing any kind of slab. You can design curved slabs, you can design irregular slabs, any kind. So thank you so much. If you have any questions, please post in the comments and I'll try to answer them. Thank you.